little drop of liquid petrol transforms into pure mechanical power to climb these massive mountains? First, the air-fuel mixture fills the cylinder. Then, the piston tightly compresses it right before the spark plug fires. Right at the peak of compression, the spark plug ignites the mix. This explosion creates the vital power stroke that pushes the piston down to keep you moving. That up and down piston pump instantly spins the engine's main gears. Then, the drive chain transfers all that raw power, and that is how a tiny bit of fuel and a 4-stroke engine can conquer these massive mountains. But to climb steep mountains, the engine shifts to first gear. A tiny gear turns a massive gear, multiplying your raw pulling power. It trades speed for raw rotational force. This extra torque is exactly what gives the back wheel enough bite to push us up the steepest slopes.
Yeah! Hunter on the prowl! Steel frame, heart made of fire. Pushing pistons ever higher. Drop the hammer, feel the roar. That 4-stroke engine begging for more. Conquer peaks and break the sky. On a torque monster, watch me fly. Watch me fly! On a torque monster, watch me fly.
To understand how a motorcycle engine generates power and utilizes gears to overcome steep inclines, we must look at the thermodynamic cycle of a 4-stroke internal combustion engine and the mechanical advantage provided by the gearbox. The 4-stroke cycle, the power source. A 4-stroke engine completes its cycle in 2 full revolutions of the crankshaft, 720 degrees. Every cycle converts chemical energy into mechanical rotation through these distinct phases. Phase, piston movement, valve status, action. 1. Intake, down, TDC to BDC. Intake open, air-fuel mixture is drawn into the cylinder. 2. Compression, up, BDC to TDC. All closed, mixture is squeezed to a high pressure/temperature. 3. Power, down, TDC to BDC. All closed. Spark ignites mixture. High pressure gases force the piston down. 4. Exhaust, up, BDC to TDC. Exhaust open. Spent combustion gases are pushed out. Key concept: the power stroke is the only phase that actually produces work. The energy generated here is transferred via a connecting rod to the crankshaft, transforming linear reciprocating motion into circular rotational motion. 2. Mechanical advantage, torque versus speed. When climbing a mountain, the engine must overcome gravitational potential energy. This requires torque, tau Wing-J, defined as the rotational force, not just speed. The gear ratio logic: the transmission acts as a torque multiplier. The relationship is governed by the ratio of the number of teeth on the gears. Low gears, first, second. A small gear on the engine side drives a significantly larger gear on the transmission output. Effect: the engine spins many times to turn the wheel only once. Result: high torque, low speed. This provides the bite required to pull the weight of the bike and rider up an incline. High gears, fifth, sixth. A larger gear drives a smaller gear. Effect: the engine spins fewer times for every wheel rotation. Result: low torque, high speed. Used for cruising on flat terrain where momentum is already established. 3. Visualizing the torque multiplier: think of the gear system as a lever. The engine input represents your effort. The gear ratio represents the length of the lever arm. If you attempt to climb a steep hill in a high gear, the lever is too short. The engine lacks the mechanical leverage to turn the rear wheel against the force of gravity, causing the engine to stall. By shifting into first gear, you extend the lever length, allowing the engine to exert massive force on the rear tire, effectively gearing down to trade high-speed potential for high-force output. This combination of the internal combustion power stroke and the mechanical multiplication of the gearbox is what allows a motorcycle to maintain forward momentum against steep grades.
Look at this bike mirror. Why do the massive snowy mountains behind me look so small yet so clear inside it?
That's because it's a convex mirror. Its surface curves outward like the back of a spoon, scattering light rays apart to create a smaller, upright image. Because the bouncing rays diverge, our brain traces them backward to form a virtual image. It looks like it's inside the mirror, allowing riders to see a huge area behind them safely.
But what happens if we flip that curve inward, like looking inside a giant cave? That's where things get really wild, with a concave mirror. Unlike convex mirrors, a concave mirror gathers all the incoming light rays and focuses them together into a single point, which focuses the light to magnify things up close. Thank you.
Oh, yeah. See the whole wide world inside this frame. Little rays of light diverge, bouncing off the silver curve. Distant mountains feel so near, chasing shadows, holding fear. It's the magic in the glass, watching all the moments pass. A tiny universe for your eye. It's the curve, a different view. Yeah, the physics in the mirror.
Amazing, right? Thanks for joining Pranavi's learning journey. Don't forget to hit follow and keep exploring with me.
To understand convex and concave mirrors, it is best to visualize them as sections of a hollow sphere. Depending on which side of the bowl is reflective, the way light behaves changes entirely. The anatomy of curved mirrors. Both mirrors rely on three key reference points. Center of curvature. C. The theoretical center of the sphere the mirror was cut from. Pole. P. The geometric center of the mirror surface. Principal axis. An imaginary line passing through C and P. 2. Concave mirrors. Converging mirrors. A concave mirror is curved inward, like the inside of a spoon or a cave. Behavior. When parallel light rays strike the surface, they reflect inward and converge at a single point called the focal point, F. Image formation. The image depends on where the object is placed. Beyond F, the image is usually real and inverted, can be projected on a screen. Between P and F, when the object is very close to the mirror, the image becomes virtual, erect, and magnified. Practical use. Used in shaving mirrors or makeup mirrors because they magnify objects when held close. They are also used in headlights to focus light into a strong parallel beam. 3. Convex mirrors, diverging mirrors. A convex mirror is curved outward, like the back of a spoon or the outside of a ball. Behavior. When parallel light rays strike the surface, they reflect outward and diverge, spread apart. If you trace these rays backward, they appear to originate from a focal point behind the mirror. Image formation. Regardless of where you place the object, the image is always virtual, cannot be caught on a screen. Erect, upright. Diminished, smaller than the actual object. Practical use. Used as rear-view mirrors in vehicles and security mirrors in shops. Because they produce a smaller upright image, they provide a wide field of view, allowing the driver to see a larger area of the road behind them. IV. Comparison summary. Feature. Concave mirror. Convex mirror. Reflective surface. Curved inward. Curved outward. Light effect. Converges rays. Diverges rays. Focal point. In front of the mirror. Behind the mirror. Typical image. Real or virtual, depending on distance. Always virtual and diminished. V. Quick visualization tip. Think of the cave. A concave mirror is like a cave. When light enters a cave, it gets concentrated, slapped inside, converging. A convex mirror is the opposite. It pushes everything away, allowing you to see a wider area at the expense of size.